Good morning, students. Welcome to Real Analysis lectures. In this lecture, we'll discuss about sequences and their convergence, and also we'll discuss about Cauchy sequence. Okay, fine. So we'll start with what is meant by a sequence. So take X is a set. Then what is meant by a sequence in X is nothing but the elements of X should be arranged in a proper way by means that means any function from n to x is called a sequence. Why? Because how elements here look like f of 1, f of 2, f of 3 and so on. Of course they all belongs to x. So this f of 1 we denote by x1 and this by x2, x3 and so on. So simply now onwards we write a sequence in x by this notation x. Okay. So any function from n to x is called a sequence in that set x. Okay, from that set x. For example, if you take it f of n which is equal to 1 by n, then the elements are nothing but 1, 1 upon 2, 1 upon 3, 1 upon 4 and so on. Okay, fine. Now we'll see some definitions. A sequence is said to be increasing, or you can also call it non-decreasing, if this is the condition that xn is less than or equal to xn plus 1 for every n. So a xn is said to be increasing if xn is less than or equal to xn plus 1, and it should be true for every n. That means what? This is same as x1. When I take n is 1, x1 should be less than or equal to x2, and when I put 2 here, n is equal to 2, this should be less than or equal to 3 and so on. Okay, we can also write the another definition, equivalent definition for increasing if, so it is, we can write it here as said to be increasing if, let me check another color, if xn is less than or equal to xm whenever n is bigger than whenever m, or you can call it whenever n, so whenever n is less than or equal to m. So whenever index are small, their values also should be small. Then we say it is increasing. Okay, you can prove that. You can take, this is suppose say definition 1 and this is definition 2. You can take a small exercise and show that definition 1 is implies definition 2 and definition 2 implies definition 1. That means whenever indexing n is less than or equal to m, then their values xn should be less than or equal to xm. Okay, fine. Similarly, you can define what is meant by a decreasing sequence. Okay, xn should be greater than or equal to xn plus 1. That is same as x1 greater than or equal to x2. Now, a sequence is said to be monotone. A sequence is said to be monotone if it is either increasing or decreasing. So, if a sequence is said to be monotone means it is either increasing or decreasing sequence. Fine. Now, let's see another definition, that a sequence is said to be bounded. So here we can quickly give some examples of increasing sequence and decreasing sequence. So here, if you want an increasing sequence, if you take xn is equal to n, then obviously it is an increasing sequence. Okay, and if you take xn is equal to 1 by n, then it is a decreasing sequence. Okay, and you can have n number of other examples. Now let's go to what is meant by a bounded sequence. Okay, a sequence is said to be bounded if the absolute values should be less than or equal to some real number. Okay, so that means what? All values, absolute values of every element in that sequence is less than or equal to some particular value. Okay, so mod xn is less than or equal to m for every n. It should be true for every element of that sequence. Then we say that it is bounded. Okay, even if one element does not satisfy, then we say that it is not bounded. But of course, if one m doesn't work, the other m may work. When we say it is unbounded, if there is no m belongs to R satisfying this condition. Okay, then we say that this sequence is unbounded sequence. If at all we can find a real number satisfying this condition, then we say that it is a bounded sequence, right? For example, here you can see that xn is equal to 1 by n is bounded because what is this value? Of course, it is positive, and we know that this is less than or equal to 1. So therefore, this is a bounded sequence, whereas xn is equal to n is unbounded because we have already seen that natural numbers is not bounded up, right? Fine. Now we go to next another definition. We are seeing all definitions, then we'll see some properties. Okay. So a sequence is said to be converged to x. Okay, so xn, and we denote this by this notation, xn converges to x if given any positive real number epsilon greater than 0. Okay, we should able to find a natural number, you can call it n, such that mod xn minus x should be less than epsilon for all n greater than or equal to n. That means after that stage, after that n naught, if you take any element from that sequence xn, their difference should be less than epsilon. Okay. So let me say it again. We say that xn converges to x if given any epsilon greater than 0, give me whatever small, maybe positive real number, we should able to find some stage after that all the elements of this sequence are close enough to x, right? This is also same as saying that xn belongs to x minus in the open interval x minus epsilon to x plus epsilon. Okay, right? If you write pictorially, suppose you assume that this is your n naught, then all xn's whatever coming here, okay, they you call it, suppose this is x minus epsilon and x plus epsilon, after all your xn's lies here only, whichever coming in this interval. Some elements of that sequence may be outside this, but only before this one. After n naught, all the elements should completely lie in this interval x minus epsilon to x plus epsilon. Okay, so roughly speaking, that there may be some elements, few elements in that sequence, they may not satisfy this condition, but after some stage, you can call it that stage as x n naught. After this stage n naught, all the elements x of that sequence should be less than distance epsilon distance, right? Okay, you can we'll see just quickly one or two examples how we can show that, how we can find that n naught is the thing. Here we'll use the Archimedean principle. For example, let's show this 1 by n converges to 0, because how you will sense that how it converges to 0, if we start writing the elements of this 1 by n sequence, 1 1 upon 2, 1 upon 3, 1 by 4, 1 by 5 and so on. So if you see that as n increases, their values are approaching to 0. So we think that after some stage all these elements are close to 0. So 1 by n should tends to 0, at least by our guess, right? Okay, intuition. How we can prove this? So take any epsilon greater than 0. What we want to show is we want to find an n naught. Okay, we want to find an n naught such that this 1 by n, that is xn minus 0, this should be less than epsilon for all n greater than or equal to n naught. So in particular, this even 1 by n naught should satisfy this condition, right? So question is, can we find an n naught satisfy this condition? Okay, if you write this one, this is same as n naught times epsilon, right? So can we find an n naught satisfying this condition? Or if I write this one, can we find an natural number n naught such that n naught times epsilon is greater than 1. This is just like your Archimedean principle or Archimedean property, that given x greater than 0 and y is any real number, we can always have a natural number satisfying this condition, right? So because our epsilon is greater than 0, so by Archimedean property there exists an n naught satisfying this condition. Okay, this is very very important. Many times we use this one. So you can say that given any positive real number, we can find a larger natural number such that 1 upon that is always less than that, however small epsilon may be, right? Then because n is bigger than or equal to n naught, 1 by n is of course less than or equal to 1 by n naught, and 1 by n naught is less than epsilon. That follows this one, right? So this is the main important thing. We have to understand how we can find an n naught. Similarly, if we take little 1 upon n plus 1, then here 1 upon n plus 1, okay, again you can check that this tends to 0. We want to show this, that means the difference we want to show that it is less than epsilon, right? So here what we show is, instead of showing 1 upon n plus 1, we will again show that 1 upon 1 by n or n naught is less than epsilon, right? Then if you take anything n bigger than or equal to n naught, then we know that 1 upon n is less than or equal to 1 upon n naught, and n plus 1 is bigger than or equal to n, so 1 by n plus 1 is this, right? That means straight away what we are getting is that 1 by n plus 1 we know is less than or equal to 1 by n naught, which is less than epsilon, right? So sometimes it may not be possible, or it is easy to show that instead of directly showing 1 upon n, whatever is given is less than epsilon, we'll try to simplify that further and show that that one is less than epsilon. Okay. Yes. So just to say, for example, you want to show 1 by n square. Okay, this instead of saying that 1 by n square is less than epsilon, just use the fact that 1 by n is less than epsilon. Okay, find such n, then use the fact that 1 upon n square is less than 1 upon n, and which is less than epsilon. So instead of directly showing that 1 by n square is less than epsilon, what we are showing is the simpler one, 1 upon n is less than epsilon, and we are using the relation among these two, right? So several times in this course we'll see such relations, right? Okay. So now we'll see some properties of this convergence sequence in R. So the first one is, if a sequence is convergent, then it is bounded. So what we are showing is that if it is a convergent sequence, then it is bounded. Okay. It is not at all difficult one. We can try to understand it. First think that what we know, that if it is convergent, then all after some stage all elements of that sequence xn, okay, they lie in this interval. So it is already there, x plus epsilon, right? And in particular you can take epsilon is 1, so this will become x minus 1 and x plus 1. Okay, so you already got an upper bound for this maximum elements, which is x plus 1, right? So this is true for all n greater than or equal to n naught. So all the elements after n naught, the xn's are less than or equal to x plus 1. This we already have. Okay, if you want, you take modulus. Okay, that is not a problem, right? Now what we want to know, only elements we want to take care about the elements of xn which are from x1 x2 up to xn naught minus 1, right? That because they are only finitely many, we can always have, whenever you have finitely many elements, you can try to find the maximum of those elements, then every element is maximum of less than or equal to that. That is the idea, right? So what we are seeing here, for epsilon 1 there exists a k or n naught, you can call it, satisfying this condition, right? Mod xn minus x is less than 1 for every n greater than or equal to k or n naught, if you whatever you want. Now you can write, because we want to show that mod xn is less than or equal to something, so we want to evaluate this value. So we can write mod xn as mod xn minus x plus x by triangle inequality. This is less than or equal to mod xn minus x plus mod x, right? Okay, this is given as x is a fixed real number, so there is no problem about this. So we want to only talk about mod xn minus x. Can we make it less than or equal to something? Okay, so because for all n greater than or equal to 1, mod n xn minus x is less than or equal to 1. So what we are getting here is mod xn is less than or equal to 1 plus mod x, but this is not true for every n. This is true for all n greater than or equal to k, right? So what is remaining is mod x1, mod x2 up to mod xk minus 1 you take. Okay, then xk onwards, we know that this is less than or equal to this value, so you put 1 plus mod x here and take m as maximum all these values. So your m is nothing but absolute values of maximum of absolute values of this swing. Then you can easily check that mod xi is less than or equal to m for every I, no matter whether it is bigger before k or after k, right? That shows that this is bounded. Okay, right? So but again I repeat, where how we are focusing is most important. How we are showing that something is convergent, we know that because of convergence, except finitely many, remaining all elements are already lying in some interval, right? So they are already having an upper bound. So what you have to bother about is that fewer elements before this. So whatever elements you have here, okay, this elements how we can control by taking the maximum of value of this and maximum value of this one, mod x plus 1, right? Okay, so every convergence sequence is bounded. What can you say about converse? Obviously not every bounded sequence is convergent. There may be many sequences which are bounded but not necessary that they are convergent. Okay, you can see that an example here. If you take xn is equal to minus 1 whole power n, how element look like? First one is minus 1 1 minus 1 1 alternative values. Okay, these things, obviously it is a bounded sequence because one is an upper bound, right? So there is no problem of boundedness. But you can see that whatever stage it may be, after any stage the elements are not at all converging to any point. They are converging, sometimes they are close to 1, but once they are close to 1 immediately they are close to minus 1, right? So you can sense that at least this, however long we go, we cannot have any stage after that they are close to some particular element, right? Because 1 then immediately minus 1 then immediately minus 1, right? So you have minus 1 here, okay, then you have 1 here. So elements are sometimes here and then sometimes here, here alternatively. Okay, so they are moving here and there, right? So we can expect at least at any stage after that stage they are all close to one particular element, right? Okay, so you can, how we can prove that? We can sense that it is not convergent, but how we will show that? Suppose assume that it converges to some x, then in particular take epsilon is 1. So for epsilon is 1, what we have here is mod xn minus x is less than 1, right? Okay, so our xn's are either 1 or minus 1. This should be true for all n greater than or equal to k, whatever stage k it may be. We know that after that even numbers will be there, again odd numbers will be there. So if you take n is equal to 2k, 2k is bigger than k, right? So at the time even value, so what you get here is 1 minus x is less than 1, right? That is same as saying that x is in the interval 0 to 2, right? So if at all this is convergent, we should, x should be in the interval 0 comma 2. And if I take n is equal to 2k plus 1 odd, then what we are getting? We are getting that n is minus, xn is minus 1. Okay, that means your x is minus 2 to 0. Okay, so how it is possible and x is in the interval 0 to 2, also x in minus 2 to 0? This is a contradiction, right? Okay, because we said that this should be there, xn minus x is less than 1 for all n greater than or equal to k. Okay, xn should be there in this interval, but here x is in 0 comma 2 as well as x is in minus 2 comma 0, which is not at all possible, right? That means this sequence is not convergent, but it is a bounded sequence. So not every bounded sequence is convergent. At least if we put some condition, can we have convergence is the question. And that is possible if we make it once our sequence along with bounded, if we put a monotone bounded sequence, then it converges. That means if a sequence is bounded and suppose if it is increasing, then also it converges, and if it is decreasing and bounded, then also it converges. That means you see that if it is already bounded, a sequence is bounded, then a sequence cannot keep on increasing. Okay, after that at least it should stop, right? That is an idea, intuitive idea, that an increasing sequence, if it is a bounded sequence, then it should converge after some stage, right? We can see what is that limit also, as well as limit here and so on, right? Okay, how we will prove this? So what we are trying to prove, that if a sequence is a monotone and bounded, so monotone plus bounded, so if we add monotone to the bounded sequence, then it will converge. This is an interesting result, and it useful many times. Okay, how we will prove this? So we'll prove it if it is a increasing sequence, then how we approach. Similar technique we can go for decreasing sequence also. Okay, so first assume that our sequence is an increasing sequence. Xn is increasing. So what is meant by Xn is increasing? Xn is less than or equal to Xn plus 1 for every n, or what is an alternate one? Xn is less than or equal to Xm for every n less than or equal to m. Okay, this is about two consecutive terms, and this is about any indexing. Whenever indexing is smaller, those values also should be smaller, right? Fine. Now because this sequence is increasing, right? Now take the range of that sequence. That means A, which is all values of that sequence. So whatever repeating, we consider only one time, that in a set, right? Because this set is already, this sequence is already given to be bounded. Our set is bounded. Okay, since Xn is bounded and it is the range of that sequence, so therefore it is bounded. So A is bounded. That means A is a non-empty subset of R which is bounded. Therefore, supremum, or you can call it LUB, exists. LUB of this set exists. Call it X is equal to, call it say X, which is LUB of A or supremum of A. We have already discussed, given notation, two notations, LUB or supremum. Okay, supremum means least upper bound, right? Now what, as I said here, if it is increasing, then it should converge to that least upper bound. So we will show that our Xn converges to X. So if at all we want to show that this Xn converges to X, which is least upper bound, you take any epsilon. How we will prove something converges? Start, take any epsilon, and we want to find some stage, natural number. After that, all these Xn's are close to X by this epsilon, right? Okay, we have already seen that X is least upper bound. What is meant by saying X is a least upper bound? If you remove any positive value from that, then this one is not an upper bound. Okay, so this is not an upper bound. We use that fact here. So whenever X is least upper bound or supremum, then X minus epsilon is no more an upper bound of that set A. Okay, you can check that, because X minus epsilon, right, we know is strictly less than X. So if at all it is an upper bound, then it is a contradiction to least upper bound property. Is this clear? So therefore this is not at all an upper bound. What is meant by saying that something is not an upper bound of a set? There exists an element K belongs to natural numbers such that, because our A is such elements, right, such that this X minus epsilon is not an upper bound, means X minus epsilon is less than X. Okay, now we have not used anywhere so far this monotone sequence definition. We have used so far up to now only boundedness, then we got here, now we will use that monotoneness, right? Because Xn is increasing, Xn and n is take n any now take any n greater than or equal to k. So n greater than or equal to k and xn is increasing means xn is greater than or equal to xk. This one you can check here, right? This one. Okay. So therefore xn is greater than or equal to xk, and we know that xk is bigger than x minus epsilon. So therefore x minus epsilon is smaller than xk and xk is greater than or equal less than or equal to xn, but all are because x is least upper bound, so they are all of course anyhow less than or equal to x, and we know x is strictly less than x plus epsilon. So if you see here, what x minus epsilon is less than x and x is less than this x plus epsilon, right? So therefore that means mod xn minus x is less than xn is less than x plus epsilon is same as saying that mod xn minus x is less than epsilon. Of course this is only true for all n greater than or equal to k. That shows that xn converges to x. Okay. Now if xn is decreasing, you can do it in two ways. One is, if a sequence is decreasing sequence in real numbers, then by multiplying with negative minus 1, what you get is minus xn is increasing. Then apply the first result, then minus xn converges to supremum of minus a, but this is same as supremum of minus a is same as minus of infimum of a. Okay, therefore xn converges to infimum. Okay, but I, instead of using this, I give you an exercise. If xn is decreasing, show that xn converges to, say, call it some y, where y is infimum of a, or this is same as greatest lower bound of a. So we already seen the concept of, just like how we have seen least upper bound, we already know that it is greatest lower bound, right? So whenever your sequence is decreasing, and that sequence is already bounded, right? So it should converge to greatest lower bound from this side. So it is greatest lower bound, right? So I, just like how we did here, the same procedure you apply. Instead of doing it for upper bound and least upper bound, now do it for lower bound and greatest lower bound. Okay, so if your y is a greatest lower bound, then epsilon is any positive real number, then just use the fact that what can you say about y plus epsilon and apply this thing. Okay, fine. So instead of this one, I ask you to prove in this way, then you can understand easy. Fine. Now we come to a subsequence. What is meant by a subsequence? Right. So this itself says, see, suppose if you have some x1, x2, x3, and so on, if it is a sequence in x, a subsequence means we somehow pick elements here again by maintaining some order. Okay, then that will be subsequence. Okay, so that means how we can represent definite this x, if we call it, this is a sequence x, so x is a map from n to x. Now we'll take any infinite subset, so S is an infinite subset of n. Okay, so we already know that any infinite subset of n, the elements of this we can represent in this form like n1, n2, okay, n3 and so on, where n1 is strictly less than n2. That means we can put it in which is smaller and which is next bigger, and so on. Any infinite subset of n, we have seen in last class, we can put it in this way, right? So therefore, when you restrict your x, this sequence, to this an infinite subset, then it is still a function, and this is called a subsequence. Okay. So what we are doing actually here is that, so what are those elements? Because this S is nothing but n1, n2, n3 and so on. So the subsequence will be denoted by xn1, xn2, xn3, xn4 and so on. Okay, so this is the subsequence which we usually denote by xnk. So xn is a sequence and xnk is also a sequence which is subsequence of that. So we are taking some elements of that sequence, but in particular, again in particular order, right? So that is the explanation which we have given here. Okay. Now you can talk about what is meant by it's the subsequence converges. Okay, that means what is meant by saying you call it suppose xn converges to x. What is the meaning of this? If for any epsilon greater than 0 there exists some n naught, right, such that mod xn minus x is less than epsilon for all n greater than or equal to n naught. So now what is meant by saying that xnk converges to x? This is the question. If again for all epsilon greater than 0 you can call it there exists some n naught, or uh, using another notation you can call it suppose some p, such that here what it will come xn. Okay, so here you can understand xnk minus x is less than epsilon for all. Instead of writing nk, it is enough if you write for all k greater than or equal to this p. Okay, this p whatever we are having, right? And how you have here you can understand by simply taking y new xnk, even though it is a subsequence, by considering as a new sequence y1 y2 y3, then if you write that definition you can understand clearly this one. Okay, fine. So you don't need to write nk greater than or equal to p. Of course, even if you write there is no problem, but it is this n in that subsequence is somehow just like fixed. In index you will write n1 n2 n3 and so on, right? So only what it is varying is this k. So what we are talking about our varying importance is this say. So that's why for all k greater than or equal to p, if mod x n k minus x is less than epsilon, then we say that that subsequence converges. Okay, fine. uh, this see, of course you can always see that this is a subsequence. Then this index, if you call it this nk, is always bigger than or equal to k for every k greater k belongs to n. That means n1 is bigger than 1, n2 is bigger than or equal to 2, n3 is bigger than 3, and so on. This in last class we have already explained by because using that well ordering principle and by having a least element property. And this is because if you take this one, then n1 less than n2 and so on, right? But because n1, what is nature smallest natural number possible, is 1, so n1 is greater than or equal to 1. Then as n1 is strictly less than n2, so n2 is strictly bigger than 1. That means n2 is at least 2, n2 is greater than or equal to 2. And if you keep on doing that, you will get that nk is greater than or equal to k, right? Okay. Now what we'll show here is this is the very interesting and the most useful result in sequence of real numbers, which says that every sequence in R, if you take any xn in R, has a monotone subsequence. Has a monotone subsequence. That means whatever sequence in R you give, we can pick elements in some proper order such that that sequence is either increasing or decreasing sequence. Okay, it is a very interesting result which says that give me any sequence in R, we can always pick a subsequence which is either increasing or is a decreasing sequence. Okay, fine. Because many times dealing with monotone sequence has advantage, because we know that a monotone sequence, once it is bounded, then it converges, right? Okay, so every sequence in R, of course we know that it is not monotone, but every sequence has a monotone subsequence, right? So how we will do this is, again I would like to explain here with an example which my teacher Professor Kumaresan always try to explain. How we construct this set, because once we construct this set, then the proof is very simple. It is all mechanical. That set is either a finite set or it is an infinite subset of n, right? So if it is a finite case, we get a subsequence. If it is an infinite case, then we get another subsequence. It is not a problem. But most of the time what as a student we do is we don't give much emphasis or focus to this set. We only by heart remember this set, and then immediately we go to next one, how we do this thing and so on. But what I feel is that then this one, how we are constructing this set, how we are how we are even thinking that such set is there is most important. Okay, so we'll try to see how we can construct such sets with an live example, then we proceed to the proof. So as my teacher always say that this is a nice example. So assume that you have a volcano is about to explore, okay, at some point, and they have predicted that at some point of time it is going to explode. Okay, so people like to see that one, but by staying some far without any damages, right? Okay, then assume that they want to see it from far but clearly visible, right? So you assume that there are some buildings, okay, infinitely many buildings, assume that nearby to that. Okay, my drawing is not so good. Okay, fine. And so on. Assume that there are so many infinitely many buildings are there. On top of that building, we go and stand there and we will watch that. Okay. So assume that this building owners they are charging so that we can go and see that. Then how people will can go and see which building we have to select to see that is the most important thing. As a viewer, which building I can select so that I can see the things without any disturbance. For example, if we think that if I stand here, then I cannot see this because of this building. My view covers this building. So this is not at all a suitable building which if at all I want to see this alkali, right? For example, this I can see it, right? Because from here directly I can see it. Or I can also select this from here, I can see this without any disturbance, right? So this is okay, this is okay. Why this is not okay? Because after this, some whatever buildings are there, those buildings height should be less than or equal to wherever you are standing, then that building is feasible. For example, if you take this building, then the height of this building and whatever building heights are there here, okay, their height is smaller than the whatever wherever you are currently standing. So I am standing right now here, okay. So whatever buildings in front of me are there, those buildings height should be less than whatever building right now I am standing, then that building we can consider for clear view, right? So how you do now, you write building numbers, you give names to buildings by say suppose 1, then 2, 3, 4, 5 and so on, right? And height of building as x1, x2, x3, x4. Then you can see that which building we have to select. That means whether we have to select building 1, 2, 3, 4, 5 is the question. That is our set S. So our set S is selecting a suitable building to watch that whatever incident we are talking about, right? And what is the condition for this suitable building is that the height of that particular building should be bigger than any other building which is in front of that, right? So that how we do it. So you say S is n belongs to n such that xn, that is height of that building, xn is height of building n, building number n. This height should be bigger than xm. What is m? Where m is the building which is in front of you, not back, in front of you, okay. So that means m is greater than n. So what is your set S? I'll select building n if the height of that current building is bigger than m for all m bigger than n. So this m greater than n says that whatever buildings are in front of you, those buildings height should be smaller than your building height currently where you are standing, right? Once you remember this, you no need to by heart, you no need to say which is greater than, whether m is here or whether n is there, all those things. Just remember this picture, which building is suitable, which building is not suitable. You never forget this set S, right? Okay, so S is nothing but all natural numbers n such that xn is greater than xm. That means the value of xn is bigger than the value of xm after you take any element after n. Okay, right? Okay, now once you have this S, then so let me write this S is again here. S is n. So xn is greater than xm whenever m is bigger than n, right? Okay. Now this is a subset of n, right? There are two possibilities, whether S may be a finite set or infinite set. So if S is a finite set, then if S is a finite set, if S is finite, that means there will only finitely many buildings are available or finitely many elements are there. We know that whenever there are only finitely many elements, we can talk about maximum among them. So maximum exists, that maximum value we denote by m. So there exists m in S such that all other elements S less than or equal to m for all S in S. Okay, is that clear? Okay. So therefore, we can select, there are natural numbers are infinite and you have only finitely many in this set S. So we can always find a natural number n1, of course, bigger than m. So n1 greater than m. This is always possible, which is such that because n1 is bigger than m and all elements of S are less than or equal to m, we can claim that. So because n1 is bigger than m, and if at all any element of S, then that should be less than or equal to m, implies that n1 is not in S. Okay. So what is meant by saying that n1 is not in S? That means that building is not suitable here means what? At least just like this third one. So at least there is one building in front of that whose height is bigger than this one, right? So that shows that there exists an n2, because n1 is not in S means there exists a building n2 whose height, okay, that means n2 is greater than n1 and xn2 height is bigger than or equal to xn1. So xn1 is less than or equal to xn2. So there is at least one building whose height is equal or bigger than that. So therefore that's why n1 is not selected, right? Fine. Now for this n2, n2 is a natural number. Again we can find another natural number, right? You can see that n2 is greater than n1 and n1 is greater than m. So therefore n2 is greater than n1 and n1 is already greater than m. So therefore n2 is also greater than m, which shows that n2 is also not in S. Okay. So therefore n2 is also not in a member of S. That means there exists again a natural number. That means there is a one more building which is in front of it whose height is bigger than that. So therefore xn2 is less than or equal to xn3. If you keep on repeating this, what you get is n1 less than n2 less than n3 such that xn1 is less than or equal to xn2 is less than or equal to xn3. So in this case, we got an increasing sequence. So if S is a finite set, then we are getting an increasing sequence of which is a subsequence. Now the second case is, suppose S is infinite. If S is infinite, then we keep applying well ordering principle n number of times, because S is a non-empty set. By well ordering principle, it has a least element, call it n1, which is the least element. So therefore n1 is less than or equal to n for all n belongs to S. That is the meaning of least element, right? Okay. Now again take the other set, which is S minus n1. From S you remove this n1 and consider this. Again it is non-empty because S is an infinite set and this is a non-empty set. So by well ordering principle, again this has a least element, call it n2. So therefore of course n2 is not equal to n1 and n1 is least. So what you get here is n1 is strictly less than n2, right? And they are of course n1 and n2, they are all elements of S. So when they are elements of S and n1 is less than n2, so what you have here is xn1 is bigger than xn2. Why? If this n1 is selected, that means the height of this one is definitely should be bigger than the height of the whatever building we have in front of us. This n2 is in front of us, so xn1 is greater than xn, right? You repeat again, take s minus n1 minus s, remove n1 n2, it is still non-empty, so therefore there is an least element n3. So what we have here is n2 less than n3 less than n3. Now take these two, in front of n2 you have n3, and n2 n3 are elements of S, so therefore xn2 height is bigger than xn3 height, right, and so on. So you get a decreasing sequence in this case, right? So if S is infinite, you get a decreasing sequence, and S is finite, at that time you are getting a increasing sequence, which is subsequence, right? So in any either case you are getting a subsequence which is monotone, right? This is one of the interesting result which says that every sequence in R has a monotone subsequence, right? Okay. And what we have proved is an important result called Bolzano-Weierstrass theorem. What Bolzano-Weierstrass theorem says that every bounded sequence, okay, if you have a bounded sequence, then this has a convergent subsequence. We already seen that bounded sequence may not be convergent, but we are proving now that every bounded sequence has a convergent subsequence. This is one version of Bolzano-Weierstrass theorem. Other version we'll see in later classes. Okay, fine. But this we already proved it by using this. If you combine this result and the previous result, we have already done it. How we did it? First, by using the fact that every sequence has a monotone subsequence. So this is a sequence. So this sequence has a monotone subsequence. This is the first step. So we can write the proof of this just now what we have proved it here. That is the first step. Then the second step, using the fact that the sequence is bounded, okay, implies that subsequence is also bounded. So what we have here is monotone and subsequence plus bounded. This one, right? And we have proved that if at all your bounded sequence is monotone, then this converges. Okay, it is monotone and bounded, so therefore it converges, right? So we have to just only use the previous two results to prove this. So take a sequence xn, which is a bounded sequence. Then by previous result, this xn has a subsequence xnk. Okay, this is a subsequence which is monotone, and because your xn is bounded, this is also bounded, and we have proved a result. If it is monotone and bounded, then it converges. That means this implies this converges, right? So every sequence in R which is bounded has a convergent subsequence. Okay, that is called Bolzano-Weierstrass theorem. Now we'll see few more results about convergence properties of convergence sequence. What it says is that every subsequence of convergence sequence is convergent. That means you have a convergence sequence and you have a subsequence, then that subsequence also converges. Okay, if your subsequence converges, then your sequence need not converge. For example, if you take minus 1 whole power n, in this you have two subsequences, minus 1 as well as 1, they converge, convergence subsequent. But this original sequence is not convergent. Okay, but what we are talking about here is the other part, which says that if your original sequence is convergent, then the subsequence also converges. Okay, and proof is not at all difficult one. You can simply go through it. Whatever substage is there, it is very simple. After some stage, every element of that xn sequence is close to x. So therefore, every element from that subsequence coming after that substage is already close to x. Is that clear? So if xn minus x is already less than epsilon for all n greater than or equal to, say, call it some. Okay, now we'll see another useful type of sequences called Cauchy sequence. Okay, so take a sequence xn. We say that xn is Cauchy if given any epsilon greater than 0. Again, we should able to find some stage such that after this stage, all the elements of that sequence should be close to each other. That means mod xn minus xm is less than epsilon for all n m greater than or equal to p. So what is the difference between Cauchy sequence and convergent? In convergent, we talk about xn's all converging to a particular element x. Okay. Whereas here in Cauchy sequence, there is no particular such element. What we are talking about is that, can you see that after some stage, all elements are close to themselves, xn and xm. If you take any two elements of that sequence, they should be close enough. That means less than epsilon after that stage. Whereas here, mod xn minus x should be less than epsilon for all n greater than or equal to p. So after that stage p, we are checking whether xn every element is close to x or not. Whereas in Cauchy sequence, what we are checking after that stage whether any two elements are close enough or not. Their difference is less than epsilon or not. Okay, this is the main difference between convergence sequence and Cauchy sequence. So in a Cauchy sequence, there is no particular x such thing, whereas you compare elements of the sequence, whereas here you compare elements of the sequence with x. Okay, we try to estimate xn with x. Here we try to estimate xn and xn. So some of the easy consequence or results of Cauchy sequence is that if it is Cauchy, then it has to be bounded. So if after some stage all elements are close to each other, then that sequence has to be a bounded sequence. That we can conclude. It is not at all a difficult one. Just like how we did for a convergence sequence is bounded, same procedure we can apply here. Instead of that xx, here you have mod xn minus xm is less than epsilon. In place of epsilon, you can take 1. There is no problem. For all n comma m greater than or equal to p. So here you try to, instead of varying two elements, we'll fix one element and we vary other. So here what we do is, in place of m greater than or equal to p, we take m is p here. Okay. So xn minus xp is less than 1 for all n greater than or equal to. So this just become like x in our convergence sequence. So all remaining proof follows as it is. Okay, that is the only step we have to make sure. So all details are here. You can go through it. Fine. Now, an interesting result about Cauchy sequence is that if at all your sequence xn is Cauchy and you have a subsequence xnk which converges to some element, then we can make sure that the original sequence also converges. Okay. Whereas if you quickly go through this result, what you have seen here, minus 1 whole power n. Okay, this has a subsequence which converges, but the original sequence is not converging. That means this is not a Cauchy sequence. This minus 1 whole power n is not a Cauchy sequence, right? So if at all it is a Cauchy sequence, then if we know that even one subsequence converges, then we can immediately conclude that the original sequence also converges to the same limit. Okay, so usefulness of Cauchy sequence. And how we prove it? By using that a Cauchy sequence, you have one condition, and a subsequence, you have another condition. By combining those two, we can easily prove it. Okay, that means there are two stages. So take a stage which is bigger than both. That is the idea. How we can do it here? You see that because it is a Cauchy sequence, so there is a P1 after P1. If you take any n and m, this is true because instead of epsilon, we are taking epsilon by 2 because we are using 2 times. That's all. Then because you have a subsequence which converges, so there is another stage P2. After that P2, this is true, right? So obviously we are going to take elements of that sequence which satisfies both. That means above P1 as well as above P2. So take P is equal to maximum of P1 and P2. Then you take any n bigger than or equal to P. What we have here is mod xn minus x. Obviously, you add and subtract this x n p, this p, whatever we got here, and use triangle inequality. You get this is less than or equal to this. Now you can check that mod xn minus xn p, because of this subsequence convergence, because k is greater than or equal to p2 and p is bigger than p, right? Okay, so what you get here is this is also less than epsilon by 2, and this also you get less than epsilon by 2. Okay, this follows from Cauchy Cauchy sequence, and this follows from convergence subsequence definition, right? So you get that this is less than epsilon. Okay, so if it is a Cauchy sequence and you have a subsequence converging to some point, then the original sequence also converges to same, right? Okay. Uh, in R or in any general, if you have a sequence, if at all it converges, okay, then it has to be Cauchy sequence. In R, we will prove that the other way is also true. Okay, that means every Cauchy sequence in R is also converges. That we will call it as completeness of R. Okay, but later onwards we'll see, we'll give some examples where in any like metric space need not be R, there you have a Cauchy sequence need not be converging. Okay, fine. So at present it is true in any not only in R, it is true everywhere. So if you have a sequence which is converging, then it is Cauchy sequence. How? Proof is not at all difficult one. You can even sense that if all elements xn's are close to x, then elements are close to each other. That is what the idea. If xn converges to x, then there exists a state such that mod xn minus x is less than epsilon by 2 for all n greater than or equal to p. Now this stage will work for us. So take n and m greater than or equal to p. Then the difference mod xn minus xm, add and subtract this x and use the triangle inequality. Okay. Then by using this fact, and here n is greater than or equal to p, so therefore this value is less than epsilon by 2 and this value is also less than epsilon by 2. So what you got is mod xn minus xm is less than epsilon. Okay, for all n comma m greater than or equal to p. That proves that if it is convergent, then it has to be Cauchy sequence. Okay, later classes we will see that not every Cauchy sequence is convergent. Okay, even you can have in Q, if you take, then in Q you can find a sequence which converges to root 2. So root 2 is not in Q. That is the idea, but that sequence is actually a Cauchy sequence, right? Fine. Now what we focus today is that in R that is true. That means in R Cauchy implies convergent, and of course convergent implies Cauchy. Okay, this is called completeness of R. So every Cauchy sequence in R converges in R itself. Okay. So how we can prove this is not at all a difficult one. We have already proved it. We use the Bolzano-Strauss theorem and so on. So take suppose quickly xn is a Cauchy sequence. Okay. Then we already know that Cauchy implies is bounded. So then we can apply Bolzano-Strauss theorem. What Bolzano-Strauss theorem says that every bounded sequence has a monotone subsequence which converges. So therefore there exists a subsequence x and k which converges to some x, right? Now just now use this previous result. What it says, that if you have a Cauchy sequence and if you have a subsequence converging to some point, then the original sequence also converges, right? So this xn is a Cauchy sequence and xnk is a subsequence of that converging to x, implies xn also converges to x, right? So it is a simple application of this Bolzano-Weierstrass theorem. It says that every Cauchy sequence in R converges, right? So in next class, we'll see nested interval theorem and other interesting results. Okay.